So till now the things are going perfectly smooth and everything is good, but some limitations comes in a figure, and that limits the further development of these BLDC motors. Okay, what are the limitations? So in that time, okay, we have Alnico that having high remanence flux density but low coercivity, okay, and it have a very high cost. And another thing that we have a Ferrite, okay, and that having low remanent flux density, and they have the whole high coercivity, okay, and has a low cost. Now the 2 points it maybe comes in your mind. What is the meaning of remanence flux density? Okay, and what is the basic concept, or what is the point that is related to the low coercivity? Okay, low and high. For the low and high, before that we have to understand the concept of coercivity and concept of remanence. Okay, then only we can understand what I'm trying to convey. And the another issue that comes in figure, the unavailability of efficient electronics. In that time duration, I'm talking about before 1980s. So before that, the electronics development is very much poor. We have we doesn't have any efficient electronic devices, and that limits us to move ahead for the further development related to the BLDC. Okay. So first we try to understand the concept of remanent and the concept of porosity. We'll just try to understand what is the concept related to the retentivity, or like remanence flux density, and porosity, or what is the basic concept that is related to that. Okay, just consider one magnetic material. As I consider the two concept, I just make two pictures. Okay. Just consider this is two Ferrite magnet that I have. Okay, in the initial condition, the internal current, like electron directions are different. Okay, and what we did, we have connected these magnets. Okay, the first section I didn't provide any type of power supply, so it's just the initial condition. And once we have connected these with some certain power supply. Okay, so what happens if we have this positive and have this negative? So always electrons try to flow from negative to positive. So the direction of electrons will be this. Okay. Okay. So if we try to understand from this particular graph, we have seen that the S-axis is basically H, which is magnetizing force, or that we can say the proportional to current, and if we are talking about the V flux density, that is proportional to the flux. Okay. So we are talking about magnetizing force is basically related to this particular power supply. So we are talking about this one, this power supply value, okay, or like the current value we are talking about. Okay, so once we are increasing the value of H, it means we are basically increasing the current. If we are basically any moment of time, what is the value of the current or H, that is get increased. So basically we are increasing the H value. Okay, and while increasing the H value, these materials are get the magnetize or get the directions. Okay, at some moment of time the material attains saturation. While increasing the current value itself, we will not get any further energization with the magnet, or any type of activity with the magnet. Okay, so then what happens? Then after that we remove this source, okay, from the magnet. Okay, then what we observe, that after removing this particular source, or whatever the like energization source that we have, after removing this one, it still attains some magnetic property. Okay, it can act as like permanent magnet. Okay. So as you can see, when we talk about this one, so while removing the input power supply or a supply, that means that the H value, what is the consideration here? The H value is basically 0. Agree? It means we doesn't have any external force or any external supply. So if it doesn't have any energization itself, the magnet or material can have some flux density. Okay, so now it's act like a permanent magnet and it has its own flux. Okay, and how much flux that it has, so that is called this BR value. Okay, so that's actually how much flux density that offers or that magnet has after magnetization. Once we remove the power, like whatever the source that you have, then you can get the value, and that value is called remanence. That value is get, what we can say, that value is get remanent flux density. Okay, the same thing. And when we talk about another perspective, once your motor, like once your magnetic material is get magnetized, okay, and here in this condition, if you can see this point, that is coercivity, B is equal to 0. What actually it means? It means your material doesn't have any type of external field. Your magnet is get demagnetized. It just act like a primary stage as initially how it act. Okay, and how it, when it is possible, when you provide negative, okay, magnetizing force or a current to the magnet, then only it get demagnetized. Okay, so once you try to demagnetize or a magnet, once you provide the negative current, then magnet get demagnetized. So what is our requirement? Why we need, just try to understand with our these two, the last slide we have seen, the Alnico. Okay, Alnico. What Alnico has, just try to see what it says. It has high remanent flux density, okay, and the low coercivity. Just try to relate with that. It has some good remanent flux density. It has some good remanent flux density. It means it can offer you high number of flux density. It means if you have this material at the cross section, the flux density that it can offer is very high. It means it's good actually. So that's a positive point. What's the negative point? That the coercive value, okay, is very much lesser. It means what happen if you have this 0 point, and just considering this one is very close to this 0 point, it means while getting very small amount of negative current or a temperature, that's also related with the temperature that we have discussed later. So once you have a temperature rise, the coercive, this particular point starts shifting toward the origin. Okay. So what happen in the, if the temperature rises, magnet get demagnetized. Okay. So what is the negative point? Either it can offer the high flux density, but what's the limitation with these magnets? That it easily get demagnetized. So that's the reason we can't use these material in our applications. So like so many applications that require very high remanent flux density, but if it doesn't have good coercivity value, that limits us to use the material or motor in a very like where we require high temperature applications, like where the applications that having high temperature, that limits our motor to be used in these type of application areas. Okay, then we talk about the ferrite. What it says is just opposite. If we have the ferrite magnet, okay, Even though it has a very good, if you can see the graph section, so it has some better coercivity value. It means like it will not easily get demagnetized. Okay, but what's the negative value? That it doesn't offer very high flux density. Okay, the V value that these materials offer is less. So by limitation of these two material, we can't use these we can't use these material to design a motor for application in which we require you can say good thermal concern points as well as good efficiency, or we required will with a high temperature with high power. Okay, Alnico deliver more power, but it doesn't support you with the high temperature rise. This will offer you less power, but it can support you with the high temperature rise, where the application that required for having the temperature sections. Okay. So these are the major cause why the BLDC or a brushless direct current motors are the developments are get stuck, or like moves in a very slow way, while unavailability of these materials. Okay. Then what's the next concern point? We have the new developments which has happened on 1980s, when the we have very different type of permanent magnets are comes in a figure, and that solves the issue that we have faced in Alnico and Ferrite. We have two new developments. Okay, these two materials are mostly comes in figure, and that's having the high remanence flux. Okay, and we have high coercivity value. So we can use these materials to design a motor in which we have a high temperature rise and where we need a very good efficiency. So both are possible by using these two segments. Mostly the neodymium iron boron, this is the mostly another way it's called also rare earth materials, like rare earth magnets, and due to their cost efficiency or like effectiveness, like it has some less price compared to other material, so we can, and as well as the availability of these materials are also good, so we can use these material in various applications. Okay. Then what next happens? The next limitation was to limitation that related to the electronic equipments. So after in this session also, like 1980s, we got some high voltage transistors which help us to enable the brushless direct current motor to generate like much power and compared to the, like you can say, the old motors. Okay, so these two developments provide a good acceleration to the BLDC motor development. Okay, and then after that in 1980s, okay, these two like in 1980s there is a first like one of the biggest BLDC motor manufactured, which is like 10 times greater power than earlier brushless direct current motor, due to these two advantages or like the new further developments that happens with the BLDC. And then after that we can see that while getting these motors having very good very good efficiency, and it can capable it is capable to use in various applications. Okay, and as we can see that today also the BLDC is much more effectively used. Same way it used 50 years later itself, it has a very vast areas where it's exploring their applications, and it's keep continuing. Let's see some major areas where we use these motors. Okay, appliances. If we talk about the appliances, we have seen some like ceiling fans, solar ceiling fans, some different type of application related to exhaust. There are a lot of applications we are using appliances. Okay, automobile, where you can see the auto rickshaw that we have, some bikes and some lot of applications we have this one. In aerospace application, in like as you can see the way in aerospace application, it's required very much precise control and all activities that we have discussed in like last few slides before. Like we have discussed this, due to their low humidity we require these type of motors, and that fulfill the requirement. When we talk about the medical equipments, in medical equipment there are a lot of requirement of motors that may use in various type of equipment like ventilation and a lot of different like equipments that we have where we need these type of motors. And the another session that like we have some industrial applications related to the like process automation, some different equipments where we need these type of motors. Okay. When we talk about the brushed DC motor or induction motor, what is the advantage of this BLDC over these two motors? How it's better than brushed DC motor and induction? When we talk about these two motors, it has better speed versus torque characteristics. Okay, in a very high speed, it can offer good torque. Okay, so like it's have a better like characteristics. Okay, then we have the high dynamic response. Okay, while we are controlling it with electronic commutation or electronic control, we have a good dynamic response, as well as its motor structure, like the rotor actually a momentary and that's a permanent magnet, so it can response very like dynamically with various applications that enable us to use these motors with applications that require very high dynamic responses. Okay, like quick start and precise control and all ideas. Okay. Then we have the high efficiency. When we talk about the high efficiency, it means that while using commutation and different type of control methodology, we reduce the losses of we remove the losses which is come to the brushed in the case of brushed DC motor, and the losses at the, like as you can see, the rotor. In the induction motor, we have the losses as a rotor to generate a counter EMF. So we doesn't require to do it in the permanent magnet synchronous motor, so like brushless direct current motor. So we have the better efficiency. Okay, and the motor doesn't have any mechanical commutation or like buses and commutation setup, so it has a long operating life. It can sustain for the long duration. Okay, and it doesn't have any mechanical section contact or anything like that, so it's a noiseless operation, and we can use these motors in very high application. Okay, so these are the major advantages that's compared with the induction motor as well as the brushed DC motor. Okay, the one more key point that I try to like convey you, like you must understand this point, that it's a very important point. These motors having torque to volume ratio is very high. What actually it means? Consider three motors. Like if we have this brushed DC motor, you have induction motor, okay, and you have BLDC motor. Okay, so, and if you consider you want to design some motor with 50 watt motor, just consider 50 watt or like okay. For brushed DC motor, the size is comparatively big compare. Okay, induction motor size is also big, and if we talk about the BLDC, the size of motor for the same power rating, the size of motor is lesser. Okay, so what it means, in a very small size, okay, we can achieve a high torque value. Okay, we can achieve high torque value with the very small size of the. Okay, so what's the advantage of this motors? So we can use these motor in places where we have a limitation with the space and the weight. In so many applications, as you can see, we have some portable devices. As you can see, the drones applications, robotics applications, some battery operated like equipments where the time, like where the size and weight is a major concern point with us. So where we can use BLDC as a new motor options that can offer you a very good torque to volume ratio, and in a very small size you can get a good torque. Okay, so this is the one of the like biggest advantage. So I'm summing up this particular video session for the what are the development, like when these brushed DC motor originated, and then what are the further developments that related to the brushed DC motor, and then how we try to look up the new options, that the limitation that comes with these brushed DC motor, and then the concept of electronic commutation comes in figure. Then how the further developments happen, what are the limitations that we have faced in the development stages, and how we come over these limitations, and till now where we are actually. Okay, we have discussed more or less. I provided you very basic ideas to understand where these motors originated and how you like try to understand the developments. Okay, so definitely that will help you to understand the motor behavior and some different aspects related to the motor. That's why I just made this video to provide you some basic idea about the origin as well as the basic development that is related to these motors. Okay, thank you for watching the video. In the next video we are trying to see like what are the basic development that is related to the permanent magnet synchronous motor. Thank you very much.